Oh, nope. There we go. Okay. So javelin throwing it, and it's dropping 2.2 meters. So here's our X. There's our Y. So Vx, delta X, T, VIY, delta Y, T, G, VFY. So really the only difference in the only difference in setup here compared to what is catching on? There we go. Between this and the ones that we did yesterday is that this VIY is not going to be 0 because we have some other angle here. Go ahead and plug in what we do know, gravity. We do know that the height, or at least the delta Y, is 2.2 meters, goes down. But after we do that and we basically write everything we know, we have to figure out Vx and VIY. So Vx is always the speed at the cosine of the angle. And let me just real quickly show you. This is really helpful. People ask, is X always go with cosine? Does Y always go with sine? For these problems, just because of the context they do, let me show you a really simple trick to figure out whether or not you're going to be using cosine or sine. So let's say you have this here. This is your X component, and this is your Y component. Let's say this is where the angle is given. And you're saying, well, instead of thinking, oh, do I have to set up tangent and think SOHCAHTOA, it's way easier than that. This is something I developed a couple of years ago. This is the x-axis. This is the y-axis. Which axis is this angle connected to? Is it connected to the x, or is it connected to the y? It's connected to the y. So the x. Why am I saying that? Because Vx will be V cosine theta. Now you're saying, well, that's always going to be the case. When we get to free body diagrams and with forces, we're going to have components of gravity because it's on an inclined plane. And there is a y component of gravity. There is an x component of gravity. But the angle that's provided is now this angle. Okay, it's now that. So that's a right triangle. So is the angle connected to the y-axis or connected to the x-axis? The y. So for this, the force of gravity in the y direction would be f of g cosine theta. Now, that's a lot better than the explanation I got when I was in high school. I got the crocodile explanation. So if you set up a triangle like a crocodile, just being totally honest, you're like a crocodile, and the crocodile, because it's a C, cosine, okay, with a C, that if it's eating the angle, the jaws close down on the axis that it's eating. I mean, like, I guess if it's closing its mouth on this axis. Whereas, like, if it was set up like this, it would be like that, and it would be closing its mouth on the y-axis. I mean, I guess it makes sense, but it's probably easier to just think which one is it connected to. There you go. That's cosine. Okay, and not having to do SOHCAHTOA. Okay, so Vx 30. And VIY, Vx is 30 cosine 52. VIY is 30 sine of 52. Oh, my calculator went out. That's right. Forgot to get my batteries. Okay. Come on, Microsoft calculator here. That is 18.47 and 23.64. That is the only difference. The fact that here that this is not 0 is the only difference here. Can't write 3s. I don't know why I can't write 3s right. Hey, we don't have enough in the x direction, okay? But we seemingly have 2 unknowns here, but this is that realization here that we don't know the time and we don't know the final velocity in the y direction. So if this is that fourth equation, second equation strategy here. Now, if you are choosing to use, how many of you are choosing to use the third equation in the quadratic? Reese, are you still doing that?
Yeah.
Okay, so but you understand how to get the final velocity from that quadratic?
Yes.
It's basically what's underneath the square root. Okay, so if you're good for that, that's totally fine. Okay, using the fourth equation first, which is this one. If I'm ever going too fast, just say, hey, can you go back there? Silence can mean, oh, we understand what we're doing, just come on, keep going. But silence can also be like, I don't know what's going on, I'm giving up, I'm just going to be quiet, I don't want to say anything. That's not what it's not the point here. Be very careful with your delta y here. In this case, if you put a positive delta y, 2.2, you wouldn't actually realize that there was a mistake because you would still get a square root of a positive number here just because of this. So be very careful. So it's plus or minus. So this is just look at this here. Plus or minus 24.54. Yes, is that the right one? Yes. Meters per second. We are choosing the negative because it's going down. Now it could possibly be positive, but it would be something where, like if you shot an arrow or something and it like stuck into a tree as it was still going upwards, that would be maybe a possibility. And then we plug it into the second equation. All right, let me check this right quick. Okay, hold on. I'll respond to that in a second here. Okay, negative 24.54 equals, not 0 as it did yesterday, equals 23.64. Careful with the algebra there. So you're going to take negative 24.54, subtract 23.64, so you're going to get an even bigger negative number. Dividing by negative 9.81 should give you a positive time. If you don't get a positive time there, that should be telling you something. It doesn't necessarily mean it's a catastrophic error. It could just be some calculation or calculator error. 4.91 seconds. It seems like a long time, but these javelins are going fairly high up into the air. I mean, if you ever watch the Olympics or World Championships, these things are going pretty high up in the air because they're floating there. So that's the time. And also the setup for this, you're like, well, how do I know what to solve for? Once you get to this x right here, this x and y, your motivation should be like, okay, yes, you want to figure out how far it goes, but you should be like, okay, I'm going to solve for time. Because once you solve for time, then it makes it more clear the route that you're going to take. Once we figure out that that is 4.91, and we know that that is 4.91, then problem becomes a lot easier here because we just have to solve for delta x, and we only have one equation there. We know it's traveling 18.47 sideways. It is doing that for a time of 4.91 seconds. .69 meters. Not the world record, but a pretty far throw for college level. The world record, I think, is 98 meters, which imagine being like at the very back of the end zone, like the very, very back where the field goal is, running forward till the point you get to the goal line, and then throwing this spear so that it goes and lands in the end zone on the other side. It's a little bit easier to do than maybe a baseball because it's more aerodynamic that it slices through the air, but that's pretty insane. I wasn't very good. I just like the novelty of trying something that, who throws javelin. I stored it in my car. I had to imagine this is a massive thing. I had to open up the left back door, and then it went from the back passenger seat in the left side over the armrest and then down into the foot part of where the passenger sat. So, yeah. People are like, "Hey, what are you doing?" And I just randomly pull out this massive javelin. And I'm like, "That's what I'm doing." All right, finding the magnitude and direction here. I'll just I'll show you the work here if you want to see the work. 18.47 squared. Make sure here that you're not, when you're finding this velocity, you're not using the initial velocity. You're using Vx, and then you're using the velocity that you just solved for. Because if you do use if you do the Pythagorean theorem on this initial information here, what are you going to get? You're going to get 30. You're going to get your initial speed. So in this case, it is going to be an angle correction. It is in the fourth quadrant. I've helped out in years past with AAU track and field state for various ages. They have javelin, and there's not a lot of kids that do it because there's no schools that do javelin. However, there is javelin for younger kids, and it's not an actual metal spear. It's basically this like Nerf elongated, almost like football looking. It's called the I think it's like the Jab Pro or something like that. It's like this big, and they basically just throw this Nerf-looking javelin down, so it's safer for kids. Okay, let's look at number 3. Okay, number 3 looks long, but it's just there's where the problem starts. The other part is just context of what's going on. Sometimes, as a teacher, it gets boring to say, "A rock is thrown." A arrow's thrown. Some girls have a clubhouse up in a tree with a sign reading "No boys allowed." Nonetheless, a younger brother of one of the girls attempts to get in. Upon being spotted, the girls throw water balloons at the brother on the ground below. Start a problem. If one of the girls throws a water balloon from the clubhouse with a velocity of 17 meters per second at 335 degrees, how high is the clubhouse, or what is delta y, if the brother is struck on his foot with a water balloon 12 meters from the base of the tree? It's a sort of a mouthful there, but if we say, like, if I was just to say, like, let's say that's, it's a side view of the clubhouse. Somebody's hanging out of here and has a water balloon that they're throwing down. They're aiming at a specific angle, but after that it starts to fall and hit the ground like that. That's what's happening there. They're not throwing it upwards. They're looking down and they're throwing it at an angle. And this is where the brother is, and they tell us that the brother's foot, when it struck, is 12 meters away from the base of the tree. This one, other than it being at an angle other than 0, is exactly the same as the Hazel marble rolling one. Because if you think about that one from yesterday, they told us how far away the cup was from the base of the table. We had to use the information to figure out how high the table is. Very similar thing here as well. Okay, plugging in what we know. We know this is 12 meters. We know gravity. This is the pertinent information up here. You're free to follow along as I go, or if you want to work at your own pace and see if we both arrive at the same conclusion. Careful, it's 335, not 355 or 353. We do get a positive Vx, which makes sense. It's moving in the positive direction to the right. We also get a negative VIY, which also makes sense because when the girl throws it, she's throwing it to the right and down. Remember, once you plug these in here, you're thinking, what is the easiest way to find the time? This is a scenario where finding the time is actually probably the easiest scenario of finding the time. Why? Yeah, it's with the x here because we have only one unknown here. We don't have to use the fourth equation to plug it in the second equation. We don't even have to, if we wanted to, use the quadratic. We already have one equation, which is Vx equals delta x over t, and we have Vx and we have delta x. Now be careful with this algebra. It's, like I said, it's not difficult, but I do see it often missed. So it's not 15.41 divided by 12. Multiply time both sides. Divide 15.41. So time is 12 divided by 15.41. That comes out to 0.78 seconds. I'm sort of going back on whether you have to box these. I guess technically you don't have to box all of these. You just have to box the answers. But if it helps you to use these problems, another part, that's totally fine. There we have the time. That is now that. And we have to find delta y. So at this point, we could solve for delta y first and then final velocity because we have to find the final velocity eventually. You could solve for final velocity first and then delta y. It doesn't really matter which way you do it because now that we have more information, we could use the third equation. So we could use this equation right here because we don't know final velocity, and that's what I'm going to use as well. But you could solve for final velocity first and then use that to solve delta y. There's more than one way here. I'm going to go ahead and use the third because that's what we did with the number 1 on the worksheet before. So
do you want us to label what direction we're on?
I would prefer, because it'll make it easier for me to kind of track where you're at. So if you just, hey, x direction, here y direction. Okay. Good, yeah. It's not required, but it makes it easier even for you. I would say going back and reviewing your work. VIY is negative 7.18. The time is 0.78. Plus 1/2 times negative 9.81 times 0.78 squared. Now with this one, you should get two negative numbers that you're adding together. This quantity is going to be a negative number. This quantity is also going to be a negative number. So you're taking a negative number plus whatever that is, negative number. So which makes sense because you're going down. Your delta y should be a negative number. I'm totally fine with you leaving what delta y is I know it talks about the height. You could totally leave what delta y is if you wanted to. You could be like, oh well, the height is, because the height is just a magnitude. It's always the same amount. So you could do either or. And then we do have to solve for the final velocity because that's what we're going to be using when we plug it into the Pythagorean theorem. It's just really completing the rest of the problem. Really, you could use the first equation to find final velocity. In the y direction, that would probably be the more difficult of them. You could use the second, as I'm doing here. You could use the fourth equation, but you would have to take the square root. So really doesn't matter. Within rounding, they should all come up to the same number. And I'll just write what the magnitude and direction is here so you can check that. Make sure that when you're finding those magnitudes that you are using the correct velocities. You should be using this Vx over here that we found at the beginning. So over there. You're not using this number. Okay, that's just going to get you back to 17. It has sped up negatively, so you use those two to find this and that. It is going to be in the fourth quadrant because it is going down. You are going to add 360. The rest of those are work you have to complete. I'd say definitely continue working on it here. Even if you just minimally saying, hey, I don't want to solve the whole problem, which I don't really know why. If you just minimally set up the X and Y charts for those. I'm going to explain number 4 real quick just to clarify something. So this is a home run from a softball player. It tells you the height of the fence. It says that the ball is hit. For the ease of here, you're going to ignore the height of the batter. Basically, you have a ball, and it's hit at a certain angle, and it's going to go up, and it's going to just barely clear the wall at that point. So you are trying to figure out how far away is the fence if the height is 1.22. And so it is, when it goes over the fence, we're stopping it here. We're not looking at what happens after that. At that point, it has gone up a distance of 1.22. So this is a positive delta y. Because if it just barely clears the fence, we don't care about it any other time, just at that point. At that point, it is higher than where it started. When I was solving this one, I was trying to make sure it was realistic. Especially, I try to be realistic, especially for people that play the sport. For example, the distance you find is actually the regulation distance of a softball field. The height is the regulation, not necessarily of all fences, but of like temporary ones. 30 degrees is the optimal angle for hitting a home run. And then so knowing the distance, I calculated back what the speed should be, and it was 28. Believe it or not, according to professionals, that is the optimal speed. Crazy how it be like that the optimal speed and angle is the best speed and angle minimum to hit a home run. So crazy how it works out like that. that they were telling me this is the minimum that you want to hit a home run, and crazy that when you actually calculate it, it comes out to be that right there. It's not just like, hey, I think that's what it should be. We're going to learn tomorrow that the optimal angle for no air resistance for most of them is actually 45 degrees. If you're trying to get the furthest in range, it's 45 degrees. When you do have air resistance, when you actually do have air resistance and effects of a ball or an object, it does change. It's usually between 30 and 50. But for example, like a javelin, the optimal angle is around 35 degrees. Because if it's going 45, it's actually what'll happen is it'll go up and it'll sort of like flatten out like that. So you want it so that it's not going sideways as it's doing that, but as it goes, it's kind of cutting through the air the whole entire time. And actually, javelin's actually complicated. The best analogy I can make for how javelins are weighted. If you want to throw further, you don't get a lighter or heavier javelin. If you want to throw further, it's where the weight is put in the javelin itself. So it's where it's distributed. For example, when I threw one, I was only throwing about 30 or 40 yards. So I think I had a 40 meter rated one, and they all weigh the same for men. They all basically weigh the same. But for something where the ruling here is that when a javelin hits the ground, it has to stick in the ground, and if it doesn't stick in the ground, it doesn't count. So even if you threw it a world record and it didn't penetrate and go into the ground, it wouldn't count. Yeah, I'll have a discussion later. I do have the answers for those ones up here as well. Sorry if the equations are kind of small there. For the left, the ones from today are the ones on the left side. In javelin, they're actually all the within a age and gender range. They're weighted so that they remember that they have to complete this arc. So if you throw it straight up here, you don't want it to just go and then fly. You don't want it to fly through the air and then land on the back of the tail, because if you think about it, it has to go it has to go up, and then it has to, over time, curve down, because even if it goes up and then lands like this, it doesn't count. So if you throw shorter, you want one that's weighted more towards the front, because by the time, since it's in the air for less time, the weight towards the front will cause it to dip earlier, whereas if you throw one that's 70 meter, you want it weighted towards the back. If somebody were to take a 40 meter rating one and try to throw it like professionals, it would actually topple over itself. It would actually might even make a complete circle and fall over. So similar to how pole vaulters have certain weighted poles for whatever their mass is and the height, that's similar in a lot. Problems you're doing up here are actually very similar. This is a problem from the AP book. There's not a picture here. I could probably draw a picture. It's a field goal try through uprights here, and you have a ball, and they tell you the initial velocity, and they tell you how far away it is here. They tell you it's 36 meters, and you have to calculate how high it is. So how high the, you have to calculate how high above the crossbar it is when it goes in, and then also, using Pythagorean theorem, figure out whether or not the ball is falling or it's still going up. So. Yeah, Reese, actually, when I do the AP problems, I do the quadratic because it is less writing.
Yeah.
And if I have a quadratic equation solver, I just boom, 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 plug it in as that.